Welcome back. Let's practice evaluating line integrals. Alright, so here's our first example. We want to evaluate the line integral along the given path, and we have the integral over the path c of x times y ds, where c is defined by the vector function, vector r of t is equal to 4ti plus 3tj, where t is between 0 and 1. Okay, so to evaluate a basic line integral, like this one right here, what we need to do is set up the line integral in terms of the parameter t that is defining the curve or the path that we are working with. In this case, we are already given the parameterization, or the vector function that represents that curve. But if that was not given to us, that would be our first step. We would need to parameterize the curve, but that won't be necessary here because we've already been given a vector function that involves the parametric equations for x and y, right? The x component of 4t would be the parametric equation for x, and the y component of 3t would be the parametric equation for y. Together, those two equations of x equals 4t and y equals 3t represent the curve that we are working with for this line integral. Okay, so the first thing that we could do here is rewrite the function that we are integrating in the line integral to be in terms of t. We know that x is equal to 4t and y is equal to 3t, so we can substitute those expressions in for x and y in the line integral, and we can also set up the bounds of integration because we know that we're working with values of t from 0 to 1. So far we have this. The line integral is equal to the integral from 0 to 1 of x, which is 4t, times y, which is 3t, and that is multiplied by ds, which in terms of t is equal to this. We will have the magnitude of the derivative of the vector function multiplied by dt. Okay, that is what ds is equal to every single time for these line integrals. And so we're not quite ready to evaluate this line integral yet. We still need to find this piece right here, the magnitude of the derivative of the vector function that represents the curve. And so in order to find that magnitude, we must first take the derivative of this vector function. So let's do that here. Vector r prime of t will be equal to 4i plus 3j. And so then we want to take the magnitude of that derivative of the vector function, and that will be equal to the square root of the sum of those components squared. So we'll have 4 squared plus 3 squared underneath that square root. 4 squared is 16, 3 squared is 9, so this is equal to the square root of 16 plus 9, which is equal to the square root of 25, which is 5. So the magnitude of the derivative of the vector function is just 5, so we can substitute that in for this magnitude right here in the line integral, and then we're ready to evaluate it. Okay, so let's do that. This would be equal to the integral from 0 to 1 of 4t times 3t. That will be 12t squared, but then we're multiplying by the magnitude of the derivative of the vector function, which is 5. So plug that in. You'll be multiplying by 5, and then that's still multiplied by dt. And so what we have here is a very basic definite integral. To just make it a little bit easier, I'll just pull the constants out to the front. 5 times 12 is 60, so this is equal to 60 times the integral from 0 to 1 of t squared dt. And we can integrate t squared using the power rule of integration. You want to add 1 to the exponent and divide by that new exponent, giving you 1/3 t cubed. And that will be evaluated from 0 to 1. And so plugging in 1, you get 1/3, and then you want to subtract plugging in 0, which will give you 0. So this evaluation is just 1/3. So this would be equal to 60 times 1/3, which is equal to 20. 20 is the final answer. That is the evaluation of this line integral of this multivariable function over this curve C. Let's take a look at another example. Next up, we once again want to evaluate the line integral along the given path. This time we're given the integral over c of x squared plus y squared plus z squared, all multiplied by ds, where the curve c is defined by this vector function. Vector r of t is equal to sine ti plus cosine tj plus 2k, where t is on the interval from 0 to 2 pi. Alright, so just like the previous example, the curve that we're working with for this line integral is already parameterized. We are given a vector function in terms of a parameter t that represents the curve, so we don't have to do that ourselves. That will not always be the case, but it is the case here again. But do notice that unlike the previous example, this is a vector function in 3 dimensions. We have an x, y, and z component, and the multivariable function that we're integrating is also in terms of 3 independent variables. Okay, so this line integral has an extra dimension than our previous example, but it doesn't really change how you approach the problem. Our goal is still the same. We want to set up this line integral in terms of the parameter t, and so in order to do that, we need to know what x, y, and z are equal to in terms of t, and those parametric equations will come directly from the vector function that represents the curve c. Right, the x component is the parametric equation for x, the y component is the parametric equation for y, and the z component is the parametric equation for z. So in this case, we know that x is equal to sine t, y is equal to cosine t, and z is equal to 2. Those are the parametric equations that represent the curve in space that we are considering for this line integral. And so we can use those parametric equations to help us start setting up the line integral. We also know that the bounds of integration in terms of t will be over this interval from t equals 0 to t equals 2 pi. So far we have this. The line integral is equal to the integral from t equals 0 to t equals 2 pi of x squared, where x is sine t, so you'll square that, you'll have sine squared t, plus y squared, and y is equal to cosine t, so squaring that, you'll have plus cosine squared t, and then we'll have plus z squared, where z is equal to 2, and 2 squared is 4. So we'll add 4, and then ds, remember that that is equal to the magnitude of the derivative of the vector function multiplied by dt. Okay, and so that's actually all we need to complete this setup and be able to evaluate the line integral. We need to know the magnitude of the derivative of the vector function. So let's find that. We have to start by taking the derivative of this vector function. And so taking that derivative, vector r prime of t will be equal to the derivative of sine t, which is cosine t. So we have cosine t I. Then the derivative of cosine t, which will be negative sine t. So we'll have minus sine t j, and then you want to take the derivative of 2, which is the z component, and the derivative of 2 is 0, so that would be 0k, which really you don't need to write down, but I'll do it anyway. I'll add 0k. All right, so that's the derivative of the vector function, and then what we need to do is take the magnitude of the derivative of the vector function, and so that will be equal to the square root of the sum of the components squared. So squaring the x component, you'll have cosine squared t, and then you'll add that to squaring negative sine t, which is the y component, and so that will become positive sine squared t, and then you could add that to the z component squared, but the z component is just 0, and 0 squared is 0, so adding 0 does not change anything underneath this square root. Okay, and so this would be the magnitude of the derivative of the vector function. It looks a little complicated at first, but remember, cosine squared plus sine squared of the same angle, in this case t, that is equal to 1. We know that from the Pythagorean identity for sine and cosine. This expression is equal to 1, so the magnitude would be equal to the square root of 1, which is just 1. So that's really nice. You can substitute that magnitude of 1 in right here in the line integral. So rewriting it here, this is equal to the integral from 0 to 2 pi of sine squared t plus cosine squared t plus 4. Notice that we have another sine squared plus cosine squared. We can use the Pythagorean identity again right here. These two terms are just equal to 1. So we have 1 plus 4 multiplied by the magnitude of the derivative of the vector function, which is 1. I'm just going to write that down. Even though it doesn't change anything, it is important to remember to include it in your line integral because it won't always be equal to 1. That is a very important piece of the line integral, so you don't want to forget it. But then what we're left with here is a very basic definite integral. In fact, it's even easier than what we had in the previous example, because 1 plus 4 is 5, times 1 is just 5. You can pull that to the front of the integral, and you have 5 times the integral from 0 to 2 pi of dt. So really you're just integrating 1 with respect to t, which will be t, so this is equal to 5 times t evaluated from 0 to 2 pi, and that evaluation will be 2 pi minus 0, which is 2 pi, so this is equal to 5 times 2 pi, which is equal to 10 pi. 10 pi is the value, or the evaluation, of this line integral for this multivariable function over this given path or curve C. For the next example, we once again want to evaluate the line integral along the given path, and we have the integral over c of x squared plus y squared multiplied by ds, where the path c is the line segment from the point -2, -1 to the point 1, 3. Okay, so first of all, we're back to working with a curve or a path in 2 dimensions. I know that because the points that the line segment is between are points in a plane. They only have x and y coordinates, and also the function that we're integrating in the line integral is only in terms of x and y. There are no z's there, so that, along with how c is defined, indicates that we are working with a line integral over a 2-dimensional path. But now, notice that the path is not already parameterized for us. We're not given a vector function, r of t, with x and y components that are the parametric equations for the curve or the path. Instead, we are just given a description of what the path is. It is a line segment between 2 points. It starts at this point, -2, -1, and ends at this point, 1, 3. So the first thing we have to do here is parameterize this path, or create a vector function that represents it in terms of a parameter t, so that we can rewrite the line integral to be in terms of that parameter t and evaluate it. And so let's work on parameterizing this line segment. And it might seem a little tricky at first, but there is a repeatable process that you can go through to parameterize a line segment between any 2 points. I'll show you the idea behind the method and then give you a little shortcut, which is the same method that I introduced in the lesson video for this topic. But here's how it's going to work. Remember that the general form for the parametric equations of a line look like this. X is equal to some constant a times t plus another constant which we represent with x sub 1. Then we have y is equal to a constant b times t plus a constant y sub 1. And then z is equal to a constant c times t plus another constant z sub 1. Now in this case, we're not working with a 3-dimensional line. Our line is in 2 dimensions, so we don't need this third equation, so I'm just going to erase it. But this is the standard form for the parametric equations of a line. And so in order to set these up for this specific line, the line between these 2 points, here's how I recommend you approach this. Every single time you want to parameterize a line segment, let the initial point correspond to t equals 0, and let the terminal point correspond to t equals 1. T equals 0 is where the line starts, and t equals 1 is where the line ends. Now you don't have to pick t equals 0 and t equals 1, but if you do, it's going to make the setup a whole lot easier. Remember that there's not just one correct way to parameterize a curve or a line segment. There are many different ways that you could do it, but I would argue that there's usually one way that's going to be easier than all the others. And so that's what I'm hoping to show you how to get here by using t equals 0 and t equals 1, because then what you can do is start solving for those unknown constants in these equations. Beginning with the x equation, we know that when t equals 0, the x coordinate must be -2. So writing that down here, for t equals 0, in this parametric equation for x, we should have -2 as the value of x, which will be equal to that constant of a times t, which is 0, plus x1. And so a times 0 will be 0, giving you that x sub 1 is equal to -2. And then you can do the same thing for t equals 1. We know that at t equals 1, the x coordinate should be 1, so you can plug those values into this parametric equation. You'll have x, which is 1, is equal to a times t, which is now 1, plus x sub 1, which we now know is -2, so you can put that right in here. We'll be subtracting 2. That's the same as adding -2. And so then solving for a times 1 is 1. So this is 1 is equal to a minus 2. You can then add 2 to both sides of the equation, and that will result in a is equal to 3. So one of our parametric equations is that x is equal to a times t, where a is 3, plus x1, which is -2. So x is equal to 3t minus 2. And then we can do the same thing for the y equation. When t equals 0, we know that the y coordinate is -1, So we can set -1 equal to b times t, where t is 0, plus y1. So we'll have -1 is equal to b times 0 plus y1. And so b times 0 is 0, meaning that y1 will be equal to -1. That's what that equation will become. So now we know the value of that constant. And then to find the value of b, we'll use the other value of t that we know. We know that when t equals 1, the y-coordinate should be 3. So we'll have 3 is equal to b times 1, that's the value of t, plus y1, which we solved for. We know that that is -1. So adding -1 is the same as subtracting 1. And so this is 3 is equal to b minus 1. Add 1 to both sides of the equation, and you'll find that b is equal to 4. So the other parametric equation will be y is equal to b times t, where b is 4. So we have 4t plus y1, which is -1. So you'll have 4t minus 1. And that completes our parametric equations. These two equations right here will represent the curve C parametrically. That is one way to find those parametric equations, but now I'm not going to use this method from here on out because there is a quicker way to do this, which is the way that I showed how to do this in my lesson video, because a quicker but equivalent way of getting these parametric equations is remembering how we would find the parametric equations of a line in space. This is something that we did towards the beginning of Calculus 3. What we would first do is find the direction vector that corresponds to that line. In other words, we would find a vector between the initial and terminal point, and that vector's x and y components would be the values of a and b, or if it had a z component, that would be the value of c. And then the other constants, x1, y1, z1, would be the coordinates of the initial point. Okay, that will give you the same exact answer, because when you use that process, you will assume that t equals 0 corresponds to the initial point and t equals 1 corresponds to the terminal point, so you will get the same set of parametric equations. And so just to demonstrate that here, if we find the direction vector for this line segment, the x component would be the difference in the x coordinates. You want to take the coordinate from the terminal point and subtract the coordinate from the initial point, so 1 minus -2 is positive 3, so you'll have 3i plus the y component, which will be the difference in the y coordinates. You'll take 3 minus -1, which will be positive 4, so you'll have 4j. And so that would be the direction vector for this line between these 2 points. And so 3, the x component, would be the value of a, which matches up with what we found for a from this method. And 4, the y component, would be the value of b, which matches up with what we found from this method as well. And then for the values of x1 and y1, those are the x and y coordinates of the initial point, which are -2 and -1, which is exactly what we found for those values from this method. Okay, so they are equivalent ways of approaching the same problem. Whether you go about it this way or using a direction vector, you're going to get the same parametric equations that represent the line segment. Just remember that when you use this shortcut method, that you have to assign t equals 0 to the initial point and t equals 1 to the terminal point. That will always be the case for that method. Okay, so from here on out in this video, when I need to parameterize a line segment, I am going to use the direction vector method because it is quicker. Although if you are more comfortable with this first method, feel free to do that instead. It does not matter. You're going to get the same answer in the end. But now we have what we need to start setting up this line integral and evaluate it. We have the parametric equations for x and y, so we can construct a vector function from those parametric equations that will represent the curve C. So let's do that. We will have that the vector function, r of t, is equal to the x component of 3t minus 2 times I, plus the y component, 4t minus 1 times j. But then in order to fully set up this line integral, remember that ds involves the magnitude of the derivative of the vector function. So let's find that. We have to start by taking the derivative of the vector function. That will be equal to 3i plus 4j. And so the magnitude of the derivative of the vector function will be equal to the square root of the sum of those components squared, which should look familiar. We had a very similar magnitude in the first example of this video. You'll have 3 squared plus 4 squared, which is 9 plus 16, which is 25. So this is equal to the square root of 25, which is 5. And so now we have everything we need to evaluate this line integral. So let's set it up. This will be equal to the integral from t equals 0 to t equals 1, right, we assigned t equals 0 to the point where the line segment starts, and we assigned t equals 1 to the point where the line segment ends. So we will integrate from t equals 0 to t equals 1. Then inside, we will have x squared plus y squared. You want to replace x and y with what they're equal to in terms of the parameter t. So for x, we'll have 3t minus 2 squared. And then for y, we'll have 4t minus 1 squared. And that will be multiplied by ds, which is the magnitude of the derivative of the vector function, times dt. So we'll have 5 times dt. I'll write that in here. We'll multiply by 5 dt, and that completes the setup for the line integral. Now all that's left to do is simplify it and then evaluate. And we do have to do a little bit of simplifying here because we have these quantities being squared that we can't really integrate in their current state. So we should expand those. And I'm going to pull this 5 to the front of the integral. So this is equal to 5 times the integral from 0 to 1 of this quantity squared. I'm going to use the shortcut to square a binomial quickly. Square the first term, multiply the two terms together, but multiplied by 2, and then square the last term. So that will result in 9t squared minus 12t plus 4. And then I'll do the same thing for this quantity. Squaring that, you'll get 16t squared minus 8t plus 1, and that's multiplied by dt. And then before integrating, you do want to combine like terms. So this is equal to 5 times the integral from 0 to 1 of 25t squared minus 20t plus 5 dt. And now we have an easier expression to integrate. And so integrating, we will get 5 times 25 thirds times t cubed minus 20 divided by 2 times t squared plus 5t evaluated from 0 to 1. And so then you want to plug in 1 for each t and subtract plugging in 0, but that will just give you 0. So just focus on plugging in 1. This will be equal to 5 times 25 thirds times 1 cubed, which is just 1, but then we are subtracting 20 divided by 2, which is 10, times t squared, which is 1 squared. So you're multiplying by 1, and then you'll add 5 times 1, which is 5. And then simplifying, negative 10 plus 5 is negative 5, and if you distribute 5 through this quantity, this will be equal to 125 thirds minus 25, and 25 in terms of thirds would be 75 thirds, and so 125 thirds minus 75 thirds is equal to 50 thirds. That right there, 50 thirds, is the evaluation of this line integral for this multivariable function over this path C. Let's move on to the next example. Hey, real quick, before we take a look at the next example, if you find my videos here at JK Math to be helpful, then I'd like to invite you to join my membership site JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out, as it's a great way to support me in the tutorials I make, as well as a great way for you to learn math better. But for now, let's take a look at the next example. Here we want to evaluate the line integral along the given path, and we have the integral over c of y squared divided by the square root of 9/16 times x squared plus 16/9 times y squared, all times ds. And the path c is counterclockwise around the ellipse represented by this equation, x squared divided by 16 plus y squared divided by 9 is equal to 1 from the point 40 to the point 0, negative 3. Okay, so just like in the previous example, the path C that we are given is not already parameterized. We will have to do that ourselves. We have to come up with the parametric equations for x and y that will represent this ellipse between these 2 points. And thankfully, that's not going to be too hard to do. Parameterizing an ellipse is very similar to how we parameterize a circle. Remember that the parametric equations for a circle will involve sine and cosine, typically we would let x be equal to the radius of the circle times cosine t, and let y be equal to the radius of the circle times sine t. And that would correspond to a counterclockwise rotation, similar to how we measure angles in the polar coordinate system, because really these parametric equations correspond to the conversion formulas from rectangular to polar. So if you wanted the opposite orientation, if you wanted clockwise rotation, you just have to swap sine and cosine. But because these parametric equations are not for a circle, but rather for an ellipse, the constants in front of cosine and sine will not be the same, because really what an ellipse is a circle where the radius is not constant, the radius changes, so this r will not be the same. Rather, those constants will be based on how much the ellipse is stretched in the x and y directions, which ultimately, those values will be based on the denominator of the x squared and y squared terms from the ellipse equation when it's in this standard form, where you have x squared divided by a constant plus y squared divided by a constant equal to 1. Okay, really you could view this as x squared divided by 4 squared plus y squared divided by 3 squared, and those values being squared will be the coefficients of cosine and sine. So we would have x is equal to 4 times cosine t, and y is equal to 3 times sine t. And if you want to see why that makes sense, if you substitute those expressions in for x and y in this equation, here's what you'll get. You'll have 4 cosine t squared divided by 16 plus 3 sine t squared divided by 9 equals 1. So in the numerator, you have 16 cosine squared t and 9 sine squared t. And then the 16s cancel out and the 9s cancel out. So you have cosine squared t plus sine squared t equals 1, which is a true statement. We know from the Pythagorean identity that cosine squared t plus sine squared t is equal to 1. So that checks out. Those will be the parametric equations that represent this ellipse. The only thing left to determine at this point is what values of t correspond to these 2 points. And to figure that out, you could plug in 4 for x right here and solve for t in this equation to get the value of t for the first point, and then you can plug in x equals 0 right here and then solve for t again to get the value of t corresponding to this point. And you would get the same thing if you used the y coordinates in this equation. But perhaps a more intuitive way to determine the values of t is to look at this curve visually. If we were to graph the ellipse in the xy plane, we can get a picture of what's going on here. This ellipse would measure out 4 in the positive and negative x directions, and 3 in the positive and negative y directions. So if this is x equals 4, x equals negative 4, y equals 3, and y equals negative 3, then the trace of the ellipse would look like this. But the actual path that we're working with here is the path counterclockwise around this ellipse from the point 4, 0 to the point 0, negative 3. So 4, 0, the initial point is this point right here, and then the terminal point 0, negative 3 would be this point down here. And the curve, or the path that we're working with, C, is not this path here. That would be a clockwise path from the initial point. Instead, the counterclockwise path heads in this direction. So the actual path, or the curve, that we're working with looks like this. And so by looking at this visually, we can determine the values of t that correspond to the initial and terminal points. You can sort of view this as a polar coordinate system in terms of how we would measure the values of t, because t would really be the angles that we would work with in a polar coordinate system. And so thinking of it in that way, an angle of 0 would be along the positive x-axis. So we're starting at an angle of 0 for a value of t equals 0, and we're ending at an angle of 3 pi divided by 2. So that corresponds to t equals 3 pi divided by 2. So we can now conclude that the values of t will be from t equals 0 to t equals 3 pi divided by 2. Or you can write it like this: t is between 0 and 3 pi divided by 2. Okay, so now we have successfully parameterized the ellipse, which is the path c for the line integral. So now let's set up the vector function that would represent c, and then take its derivative and find the magnitude of that derivative so that we can set up and evaluate this line integral. Starting with the vector function, r of t, that will be equal to the x component of 4 cosine t times I, plus the y component of 3 sine t times j. But then let's take the derivative of that vector function. That will be equal to the derivative of 4 cosine t. The derivative of cosine is negative sine, so you'll get negative 4 sine t times I, and then you'll add that to the derivative of 3 sine t, and the derivative of sine is cosine, so you get 3 cosine t times j. Now let's take the magnitude of the derivative of the vector function. That will be equal to the square root of the sum of the components squared. And so squaring the x component, you'll get 16 sine squared t, and then you'll add squaring the y component, which will be 9 times cosine squared t. And that doesn't really simplify any further. We can't use the Pythagorean identity here because sine squared t and cosine squared t have different constant multiples, so we can't pull anything out. Instead, we have to leave the magnitude like this. There's nothing that we can do to change it. But now we do have everything we need to set up the line integral. So let's start working on that. This will be equal to the integral from t equals 0 to t equals 3 pi divided by 2. Those will be the bounds of integration. 0 is the lower bound, and 3 pi divided by 2 is the upper bound. And then we need to rewrite this function to be in terms of the parameter t. So let's replace y with 3 sine t and square it. That will give us 9 sine squared t, and then that will be divided by this denominator, which looks pretty complex at first, but it will work out very nicely. As you're going to see, we have the square root of 9/16 times x squared, but x squared would be 4 cosine t quantity squared, which will be 16 times cosine squared t. So those 16s will cancel out, right? 16 divided by 16 is 1, which will just leave you with 9 times cosine squared t. So I'll just write that. We have 9 times cosine squared t plus 16/9 times y squared, which we know is 9 sine squared t. So you're multiplying by 9 sine squared t, but then those 9s will cancel out, leaving you with 16 times sine squared t. So we have 16 sine squared t, and then we're multiplying that expression by ds, which is the magnitude of the derivative of the vector function multiplied by dt. So let's write that in here. We're multiplying by that magnitude, which is the square root of 16 sine squared t plus 9 cosine squared t, and that will be multiplied by dt. And so right now this integral looks pretty nasty. However, this magnitude will cancel out with this denominator. They are the exact same expressions. The order of the addition under the square root is reversed, but that doesn't matter. The order of addition doesn't matter. You can add 2 plus 1 or 1 plus 2. You're still going to get 3. The same is true for these expressions, so those two expressions are the same. They will cancel out, just leaving you with the integral from 0 to 3 pi divided by 2 of 9 sine squared t dt. And that is a trigonometric integral that we know how to solve. We learned how to evaluate this in calculus 2. So let's work on that now. Remember that in order to integrate sine squared t, what you need to do is rewrite it using a particular trig identity. It looked like this. I'll start by pulling that 9 out to the front. We have 9 times the integral from 0 to 3 pi divided by 2 of sine squared t, which we'll rewrite with 1/2 times 1 minus cosine of 2t dt. That is a double angle identity for sine squared t. Rewriting it in this way allows us to actually integrate that expression. So then what you want to do is pull out that 1/2, split up the integral into two pieces. We'll integrate 1 and cosine of 2t separately. This is equal to 9/2 times the integral from 0 to 3 pi divided by 2 of 1 dt. So I'll just write that as dt. And then you are subtracting 9/2 times the integral from 0 to 3 pi divided by 2 of cosine of 2t dt. Now, in order to integrate cosine of 2t, you would technically need to use a u substitution. You would set 2t equal to u, but then from that whole process, you would need to introduce a 1/2. So I am just going to skip that work. The result of that integral will be 1/2 times sine of 2t. I'm hoping by this point you're used to integrating an expression like this, so I'm just going to skip that u substitution because it does take a little bit of time to write out. So what we get here is this. We do also need to integrate 1, but that's just equal to t. So this is equal to 9 halves times t evaluated from 0 to 3 pi divided by 2 minus 9 halves times 1 half sine of 2t evaluated from 0 to 3 pi divided by 2. Okay, again, 1 half sine of 2t is the integral of cosine of 2t. You can find that using a u substitution. But then, evaluating, t evaluated at 3 pi divided by 2 minus the evaluation at 0 will just be 3 pi divided by 2. So we'll have 9 halves times 3 pi divided by 2. And then for this integral, if you evaluate sine of 2t at 3 pi divided by 2, those 2's will cancel out, and you'll just be evaluating sine at 3 pi, which is 0, and then you'll be subtracting evaluating sine of 2t, where t is 0, so you'll just have sine of 0, which is also 0. So this entire term just becomes 0. Okay, the evaluation results in 0, so all we have left is 9 halves times 3 pi divided by 2, which simplifies to 27 pi divided by 4. And that doesn't simplify any further, so that is the final answer to this example. 27 pi divided by 4 is the value of this line integral given this path C. Next up, we want to evaluate the line integral along the given path, and we have the integral over C of the quantity x plus 4 times the square root of y times ds, where the path C is counterclockwise around the triangle with vertices 0, 0, 1, 0, and 0, 1. Okay, so we have a different type of path than what we've had in previous examples, although it does share some similarities with something that we've already done. I'll talk about that in just a moment, but I think the first thing that we should do here is draw a picture, or essentially graph, this path. And so it is a path in a plane. All these points are 2D points that are the vertices of a triangle, so we can sketch that in a plane. Let's sketch it in the xy plane. I'll start by plotting the 3 vertices. We have 0, 0, which is the origin, along with the point 1, 0, and 0, 1. So I'll let this be x equals 1 and y equals 1. So then the point 1, 0 is right here, and the point 0, 1 is right here. So then connecting those 3 points, we have the triangle. But don't forget about the orientation. The orientation is counterclockwise, so from any vertex of the triangle, we would be traveling in a counterclockwise direction. But what's important to notice here about this path is that it is not one continuous smooth curve, right? This path is broken up into 3 pieces. There are these sharp points, which are the vertices of the triangle, that sort of break up the path. And so when you have a path like this, that is not a continuous smooth curve, in order to actually evaluate the line integral, you want to split up that path into separate paths. Particularly, you want to split it up into pieces where each piece on its own is a smooth curve or a smooth path. In this case, everything is lines, so they're not really curves, but you get the idea. We have 3 different sections or 3 different pieces of this path that would be considered as smooth on their own, but together they would have sharp points that make it not smooth. Okay, and so since we're going to break it up, I'm going to label each of those paths to be a different path. I'll label this horizontal line as the path C1, I'll label this slanted path as the path C2, and then this vertical path will be C3. And so together the path C would be equal to C1 plus C2 plus C3, but we have to split it up this way in order to actually evaluate this line integral. In fact, what we have to do here to evaluate this line integral is calculate 3 line integrals and take their sum. We'll calculate a line integral for C1, then another one for C2, and another one for C3, and add their results together. That will look like this. Okay, so really our work here has tripled compared to previous examples. We have 3 different paths that we need to parameterize in order to set up these line integrals in terms of t and evaluate. Okay, so that does seem like it's going to be a lot of work, but all 3 of these paths are line segments, so they're not too bad to parameterize. I showed you a shortcut method for quickly parameterizing a line segment in a previous example. We are going to use that same method here. All 3 of these line segments are 2D lines, so we can use the parametric equations for a line that x is equal to a times t plus x1, and y is equal to b times t plus y1, where a and b are the x and y components of a direction vector for the line, and x1 and y1 are the x and y coordinates of the initial point for that line. And of course, this is assuming that you are letting the initial point of the line correspond to t equals 0 and the terminal point correspond to t equals 1. Okay, so let's start setting up these parametric equations for each of these lines. I'll begin with C1. For C1, that line segment is traveling from the point 0, 0 to the point 1, 0. So 0, 0 will correspond to t equals 0. That's the initial point, and 1, 0 will correspond to t equals 1. That is the terminal point. So then the direction vector, vector v, we can find that by taking the difference in the x and y coordinates. For the x component of the vector, you'll subtract the x coordinates. 1 minus 0 is 1, so you'll just have 1i. And then for the y component, you'll subtract the y coordinates, and 0 minus 0 is 0. So you would add 0j, but I'm not going to bother to write that here. V equals I will be the direction vector for that line. And so we can use that along with the initial point to help us set up the parametric equations for that line. We'll have x is equal to a times t. A, the x component of the direction vector, is 1. So you just have 1 times t. And then you want to add the x coordinate of the initial point, which is 0. So you just get x equals t. Then for the equation for y, you'll have y is equal to b times t. B would be equal to 0. The y component of the direction vector is 0. And y1 would also be 0. The y coordinate of the initial point is 0. So you have y equals 0 plus 0, which is 0. So those are the parametric equations for this line. You can create a vector function using those parametric equations. You'll have r of t is equal to t times I, and that's it. We have now parameterized C1. Now let's move on to C2. That's going to be a slightly trickier line, but we'll still follow the same process. This time for C2, the line segment starts at the point 1, 0 and ends at the point 0, 1. Which means this time around, and this is a new set of t values, these are separate from the t values for C1. We do not need to take those into account. I'm just going to let t equals 0 correspond to the initial point, and t equals 1 correspond to the terminal point. And so then the direction vector for this line segment, let's find those components. Starting with the x component, you'll take 0 minus 1, which is negative 1. So you'll have negative I plus the y component, so you'll take the difference in the y coordinates, and 1 minus 0 is 1. So you'll have positive j. And so that's the direction vector. You can then use those components to set up the parametric equations for that line. Starting with x, we'll have x is equal to a times t. A is negative 1, so you'll have negative t plus the x coordinate of the initial point, which is 1. So you'll have negative t plus 1. And then for y, you'll have y is equal to b times t, where b is positive 1. So that will just give you t plus the y coordinate of the initial point, which is 0. So you'll just have y equals t, meaning that the vector function for this part of the path will have an x component of negative t plus 1. That will be multiplied by I, and then we'll have t times j. And just to differentiate these two vector functions so that you know which paths they correspond to, I'll let this be vector r sub 1 and vector r sub 2. Okay, just to make sure that that's clear. But then let's move on to the final path, path C3. This path begins at the point 0, 1 and ends at the origin 0, 0. So this time around, t equals 0 corresponds to 0, 1, and t equals 1 corresponds to 0, 0. Again, this is a different set of t values than what we used for C1 and C2. So it's okay that we're using the same values because they are not related to one another. We're treating these three paths as separate paths. Okay, but then for the direction vector of this line, starting with the x component, look to the x coordinates. You'll have 0 minus 0, which is 0. So the x component is 0. So let's just move on to the y component. Looking at the y coordinates, you'll have 0 minus 1, which is negative 1. So you'll have negative j for the direction vector. And so using that to set up the parametric equations, x will just be equal to 0 because a, the x component of the direction vector, is 0. And then the x coordinate of the initial point is also 0. So x is just equal to 0, and then y is equal to b times t, where b is negative 1, so we'll have negative t plus the y coordinate of the initial point, which is 1. So you'll have negative t plus 1. And so the vector function for the path C3, which I'll call vector r sub 3, that will be equal to 0i plus negative t plus 1j. And now we're done parameterizing all three parts of this path C. We can now use these three vector functions to help us set up these three line integrals that will add together to be equal to this line integral. Okay, and so let's work on that setup. Remember that for each of these integrals, that ds will involve the magnitude of the derivative of the vector function. So actually, before we set anything up, I do want to take the derivative of each of these vector functions, starting with the derivative of vector r1, that will be equal to I. Then for vector r2, the derivative of that will be equal to negative I plus j. Then finally, for vector r3, the derivative of that vector function will be equal to negative j. And so now that we have those derivatives, we can find their magnitudes and insert those into these line integrals. I'm actually going to calculate those magnitudes within the line integrals just to save some time and space. Starting with the line integral for C1, we will be integrating from t equals 0 to t equals 1. In fact, we'll be doing that for all three of these integrals. So we will have that this is equal to the integral from 0 to 1 of x plus 4 times the square root of y. We need to replace x and y with what they're equal to in terms of t. And for C1, x is equal to t and y is equal to 0. So this term is just gone. We're just going to be integrating x, which is t. So really, I don't need this parenthesis at all. We'll just have t times ds, which will include the magnitude of the derivative of the vector function. So we're multiplying by the square root of the sum of these components squared, but there's only one component. We have an x component of 1, so we're taking the square root of 1 squared, which will just be 1, but I'll leave it like that for now. That will be multiplied by dt. Then we're adding that to the line integral for C2, where once again, we're integrating from t equals 0 to t equals 1. So write those bounds in. And then this time around, x is not just equal to t. We're now working with path C2, where x is equal to negative t plus 1. So replace x with that. We'll have negative t plus 1 plus 4 times the square root of y, where y is now equal to t. Not 0, because we're working with C2. So you'll have 4 times the square root of t, and that will be multiplied by the magnitude of the derivative of the vector function. And so you want to take the square root of this sum of these components squared. Negative 1 squared is 1, and 1 squared is 1, so you'll have 1 plus 1, which is 2. So you'll be multiplying by the square root of 2, and then dt. And then let's add that to the last line integral for C3, where we are once again integrating from t equals 0 to t equals 1. So write those bounds in. And then rewriting the function in terms of t. This time around, x is equal to 0, so that term is gone. We're just going to have 4 times the square root of y, which is negative t plus 1, which just to make it a little bit easier to write, I'll reverse that order and write it as 1 minus t. It's the same thing, just looks a little bit nicer. But then don't forget to multiply that by the magnitude of the derivative of the vector function. So take the square root of the sum of the components squared. In this case, there's only one component of negative 1. Negative 1 squared is 1. So you will be multiplying by the square root of 1 times dt. All right, and so now we have all the line integrals set up. All that's left to do now is evaluate them and add them together. So let's work on that. Starting over here, the square root of 1 squared is just 1. So you're multiplying t by 1. This is just equal to the integral from 0 to 1 of t dt. Then for this integral, I'll pull the square root of 2 out to the front. We'll have plus the square root of 2 times the integral from 0 to 1 of these terms, which are not too bad to integrate, although I will rewrite the square root of t as t to the 1/2 power, and also I'll reorder these terms. I'll write it like this. We'll have 1 minus t plus 4 times t to the 1/2 power, so that is then ready to integrate. And then for this last integral, the square root of 1 is 1, so you're just multiplying this by 1, and I'll pull that 4 out to the front, so we have plus 4 times the integral from 0 to 1 of the square root of 1 minus t dt. Now this is an integral that does require the use of u substitution. You would want to set u equal to that inside function of 1 minus t. If you do that, and I'll write it on the side here really quick, if you let u equal 1 minus t, then du dt, the derivative, is -1. So du equals negative dt, but I don't see a negative dt in the integral. I just see a positive dt. So I'll multiply both sides by -1, and the substitution here will be negative du equals dt. Okay, so we'll come back to that. Let's begin integrating these other integrals. This is going to be equal to 1/2 t squared evaluated from 0 to 1. That's just using the power rule of integration, which we're going to use again for this next integral. We have the square root of 2 times t minus 1/2 t squared plus 4 times 2/3 times t to the 3/2 power evaluated from 0 to 1 plus 4 times the integral, and if you want, you can rewrite those bounds in terms of u, plugging in 0 for t, 1 minus 0 is 1. So the lower bound is now 1, and then the upper bound of 1, plugging that in, 1 minus 1 is 0. So the new upper bound is 0 in terms of u, and then you have the square root of u times negative du. Okay, but then we can get rid of that negative. I don't like integrating from 1 to 0. I'd rather integrate from 0 to 1. So if I flip those bounds of integration, that will negate the integral, which will get rid of that negative. Okay, so let's do that. This will be equal to 1/2, right? T squared evaluated at 1 is just 1, and then evaluating at 0 is just 0. So you get 1/2 times 1, which is 1/2, and then you'll have plus the square root of 2 times this expression evaluated at 1 minus the expression at 0, which will just be 0. So just focus on plugging in 1. You'll get 1 minus 1/2 times 1 squared, which is 1/2, plus 4 times 2/3 is 8/3 times 1 to the 3/2 power, which is 1. So that's just 8/3. And then you'll add that to 4 times the integral from 0 to 1 of u to the 1/2 power du. But then integrating that and simplifying the other pieces, we have 1/2 plus the square root of 2 times 1 minus 1/2 is 1/2. 1/2 plus 8/3. If you get a common denominator, you should get 19/6. And then we're adding 4 times the integral of u to the 1/2 power, which will be 2/3 times u to the 3/2 power, evaluated from 0 to 1. And that evaluation will just be 2/3. So this is equal to 2/3 times 4, which is 8/3. So finalizing the answer up here, this is equal to 1/2 plus 19 square roots of 2 divided by 6 plus 8/3. And so getting a common denominator between these three fractions and adding them together, you will get 19 plus 19 square roots of 2 divided by 6. And if you wanted to, you could pull out that common factor of 19 out of those two terms in the numerator, but it doesn't matter. That would be the final answer to this example. 19 plus 19 square roots of 2 divided by 6 is the value of this line integral over this path. Let's take a look at one more example for this video. For our last example, we want to evaluate the line integral along the given path, and we have the integral over c of x times y times z squared times ds, where c is the line segment from 220 to 342. Okay, so this is very similar to a problem that we did earlier in this video, but instead of our path being a line segment in 2 dimensions, this is a line segment in 3 dimensions. Not to mention that the function that we're integrating in the line integral is also a multivariable function of 3 independent variables, x, y, and z. Okay, but even so, the process remains the same. The first thing we want to do here is parameterize this path or this line segment, and we're going to use the same method that we have used for other line segments in other problems. I always recommend that you let t equals 0 correspond to the initial point and t equals 1 correspond to the terminal point, because then you can use the shortcut of finding a direction vector between these 2 points and using the coordinates of the initial point and the components of that direction vector to set up the parametric equations for a line in space. Okay, so let's start by finding that direction vector, vector v. The x component will be the difference in the x coordinates between the terminal and initial point. You'll take 3 minus 2, which is 1. That's just equal to I. Then that will be added to the y component. So take the difference in the y coordinates. 4 minus 2 is 2. So you'll have 2j. And then for the z component, take the difference in the z coordinates. And 2 minus 0 is 2. So we get 2k. All right, so then from that direction vector and the coordinates of the initial point, we can set up the parametric equations that will represent this line segment. We'll have x is equal to a, which is 1, times t, plus x1, which is 2. So you have t plus 2. Then y will be equal to b, which is 2, times t, plus y1, which is 2. So you'll have 2t plus 2. And then you'll have z is equal to c, which is 2, times t plus z1, which is 0, so you'll just have 2t. Okay, so the vector function that we will use to represent this path or to parameterize that line segment will have an x component of t plus 2, a y component of 2t plus 2, and a z component of 2t. And so then let's just move right into taking the derivative of this vector function and finding its magnitude. That way we have that ready to go when we set up this line integral and evaluate, starting with the derivative of the vector function. The derivative of the x component will just be 1. You'll get I plus the derivative of the y component, which will just be 2. So you'll have 2j. And then you'll get the same thing for the z component. The derivative of 2t is 2. So you'll have plus 2k. All right, so that's the derivative of the vector function. But then taking the magnitude of it, you want to take the square root of the sum of the components squared. So you'll have 1 squared plus 2 squared plus 2 squared, which is 1 plus 4 plus 4. That equals the square root of 9, which is 3. And now we have everything we need to set up and evaluate this line integral. So let's do that. This will be equal to the integral from t equals 0 to t equals 1. And then rewrite this function in terms of t, replace x, y, and z with their parametric equations. So x is t plus 2, y is 2t plus 2, and z is 2t, so we'll have 2t squared. And then you're multiplying by ds, which will be the magnitude of the derivative of the vector function, times dt. So we'll be multiplying by 3, and then dt. All right, so now the line integral is all set up. We just now need to simplify it and then integrate and evaluate. So let's work on that here. I am going to pull this 3 out to the front, and then I'm going to multiply these two factors together. So that will look like this. We'll have 3 times the integral from 0 to 1 of t times 2t is 2t squared. Then you'll take t times 2, which gives you 2t. Then you'll multiply 2 by 2t, which will give you 4t. And then multiply 2 by 2, and you'll get plus 4. And that will be multiplied by 2t squared, which will be 4t squared, and then you have dt. All right, now I'm going to pull that 4 out to the front, and then combine these two like terms of 2t and 4t. So this is equal to 3 times 4, which is 12, times the integral from 0 to 1. And then I do want to distribute this t squared through this quantity as well. I'll do that at the same time as combining these like terms. You'll have 2t to the power of 4. Then you'll have 6t times t squared, which becomes 6t cubed. And then you'll add that to 4 times t squared, which is 4t squared. All right, then that's multiplied by dt. And now we're ready to integrate. This is equal to 12 times the integral of each of these terms using the power rule of integration. So we'll have 2/5 times t to the power of 5 plus 6/4 times t to the power of 4 plus 4/3 times t to the power of 3, evaluated from 0 to 1. And so then evaluating, I'll do that up here. You want to plug in 1 and then subtract plugging in 0, but plugging in 0 will just give you 0. So just focus on plugging in 1, and 1 to the power of 5, the power of 4, or the power of 3 is just 1. So this is equal to 12 times 2/5 plus 6/4, which reduces to 3/2, and that will be added to 4/3. All right, so then if you get a common denominator between these three fractions and add them together, you should get 12 times 97 divided by 30, which simplifies to 194 divided by 5. And that right there is the final answer to this example. That is the value of this line integral over this path that is a 3D line segment. And so with that, that is it for this example. And this was also the last example for this video. But if you do want to get some more practice, I have another available on my membership site. So if that's something that interests you, feel free to look into becoming a member. You can find all the details on my website at jkmathematics.com/plus. If you have any questions, please let me know in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.